So another kind of constrained motion example, and we've already seen an example of this kind, is when some particle moves along a wire of a particular shape. So earlier, I think we looked at when the particle moved along a straight line, but now let's say we want to look at the particle moving in a circle like so. So the equation of the circle is given to be x plus y equal to 5. Okay. Imagine, for instance, that the particle was moving on a straight line of the form x plus y equal to 5 instead of the squares. Then x dot and y dot would be related by, you just differentiate that equation and you get x dot equals minus y dot. Okay, but now we have, these squares. Okay, that's the difference. And we want to say determine a relationship between x, y, x dot, and y dot. So between basically the velocities, but the position will also show up, unfortunately. Similarly, we want to find a relationship between the acceleration in the x and y directions by virtue of this object moving in a circle. But that expression will also depend on, it turns out, the current position and the current velocity. Okay. So how do we do this? So part A, we want to determine essentially a relationship between the positions and the velocities. To get velocities from these positions, what's the next step? Of course, the next step is to differentiate. We differentiate one, right? So we say d by dt of x square, so differentiate with respect to time, because x dot and y dot are time derivatives, equal to d by dt of 5 equal to 0, okay? Because d by dt of a constant is 0. Now what is d by dt of x squared plus y squared? Okay, so x is not, well, x is different from t, it's a different variable. Similarly, y is a different variable. So recall essentially chain rule. So d by dt of, say, some function f of x is going to be partial derivative of f with respect to x, or well, it doesn't have to be partial derivative, I guess, because it's just a function of x, df by dx and then dx by dt. Okay, so that's basically d by dt of f of x. Similarly, d by dt of some other function g of y is going to be dg by dy, dy by dt. Okay, sounds good? Okay, let's use these things now. So let's call this equation number 2. So basically, dx squared by dt equals dx squared by dx times dx by dt. Okay, so we're just using this chain rule here. So d by dx of x squared is 2x, and then dx by dt is just x dot. Similarly, d by dt of y squared equals d by dy of y squared times dy by dt. Sort of using this equation here now. That's going to be equal to 2y times y dot. Okay, so we call this 3, call this 4, use 3 and 4 in 2. So basically we have um, 2 is basically d by dt of x squared plus y squared equal to 0, and then when we plug in 3 and 4 in there, we get 2x x dot plus 2y y dot equal to 0. 2 gets cancelled, and we get x dot plus y dot equal to 0. Okay, so that's one equation. And this is part A. This is the answer for part A. So recall, part A asked for a relationship between x, y, x dot, and y dot. And this is what that is. Okay, so if you know the current position x comma y and the current velocity in the x direction, you can compute the current velocity in the y direction or vice versa. So given 3, can find the fourth variable. And then part B asks for find relation between x, y, x dot, y dot, and most of all x double dot, y double dot. How do we do this? Well, first of all, let's call this equation number 5. Because this question relates the accelerations in the x and y direction, we basically need to differentiate this equation. Now, how do we differentiate this equation? We have to use something very similar to here. Okay. Unfortunately, we have x, it's not a function of x here, it's a function of x and x dot. Similarly, it's a function of y and y dot. So recall multivariate chain rule. Chain rule. So if you have some function, let's say h of p comma q, and then we say d by dt of p comma q, then the expression for this is partial derivative of h with respect to p times dp by dt plus partial derivative of h with respect to q times dq by dt. So corresponding to that, if we say what is the derivative of x dot, that's basically partial derivative. So basically you can think of x dot as h of p comma q, where p is x and q is x dot. Okay, so you can think of this basically as pq. So basically this is dh by dp, dp by dt. Let me just write it in terms of x and x dot. Well, let me just leave it as p and q, and then finally replace it. And then partial pq divided by q times dq by dt, and dpq by dp is basically q, dp by dt is p dot, and then this gives us d of pq by q is basically p, and this is q dot. And recalling that p is x and q is x dot, you can plug this in here. You have x dot, p dot is going to be x double dot because p itself is x, and then p is x, q dot is, yes, p dot is x dot, and then q dot is x double dot because q itself is x dot. So basically we have d by dt of x dot is this quantity, okay? X dot square plus x double dot. Similarly, we can show d by dt of y dot equals y dot square plus y double dot. And then basically we go differentiating 5. We have d by dt of xx dot plus y dot equal to 0, which is the same as x dot square plus x double dot plus y dot square plus y double dot equal to 0. Okay, so just plugging these two things into here, and this is the answer for part B. It has to do with this chain rule. Okay, this chain rule you want to try to understand. If you have a function of two variables, p and q, in this case p and q are x and x dot, you basically differentiate this expression with respect to p. It's a partial derivative because when you differentiate it, you're thinking of the other thing as a constant, essentially. dp by dq, dpq by dp, which is basically q, times dp by dt, and dpq by dq, which is p, and so on, right? So this is the chain rule. This is the multivariate chain rule, okay? Multivariate meaning if you're differentiating two variables, a function of two variables with respect to a third variable, what is the derivative? This is what that looks like, okay? This is a bit more of an advanced sort of problem. Your last homework problem might be very, very similar to this. So that's why we sort of worked this out. Let's stop that here for now. Any questions?